What's up everybody, welcome to another video, and I hope you're ready to flex those brain muscles. In this video we're going to practice finding complex roots using DeMoivre's theorem. So I'm going to start by just talking about this formula a little bit, then we're going to jump into two examples, and hopefully you find this video helpful. So first let's talk a little bit about this formula, and what I want to first point out is that in order to use this formula, we have to have the number we're finding the roots of in polar form. As you'll notice here, this W, this is the number that we're going to find the roots of, and it's written in polar form, and that's where our R and our theta come from in this formula, is from that number in polar form. So that's often our first step that we have to do before we really even use this formula, because usually we're asked to find the complex roots of a number that isn't given in polar form, like this first example here, right? So first thing we're going to do is convert this to polar form, then we can start using this formula. Next couple things I want to point out are this n. Where does n come from? So n is the type of roots we are being asked to find. So in the case of this first example, we're being asked to find all of the complex fourth roots of this number. So our n is going to be 4, right? And there are going to be 4 distinct fourth roots of this number. And that's always true. If we're asked to find cube roots, then our n is going to be 3, and there are going to be 3 distinct roots. Those always line up, okay? So once we have r, theta, and we've identified n, we can plug all that into this formula, and then the only thing that changes throughout using this formula is k, right? And that's how we get each of our roots. We start with k equals 0, that gives us our first root. Then we do 1, that gives us our second root, and we continue until we find all of our roots, right? And that's why we always end up stopping 1 short of whatever our n is, and really it's just because we start this counting process at 0, right? So with my fourth roots, with this first example, I'm going to do 0, 1, 2, and 3. And those values for k are going to give me my 4 distinct fourth roots. So hopefully that makes sense. This formula can be a little intimidating at first. It really just takes some practice getting used to it. Last thing I want to point out is there are different forms you can see this formula written in. Sometimes you'll see this combined into one single term, right? These common denominators, though this will be combined. Sometimes you'll see it written in degrees, and actually that's the last thing I really want to point out before we jump into this first example, is that I actually prefer using degrees with these kind of problems simply because we get to avoid dividing fractions and finding common denominators and that kind of stuff that comes along with using radians. So if you are going to use degrees, then really you just have to rewrite this, and instead of 2 pi, we have 360 degrees. So this will be 360 degrees k over n, and that will replace both of these terms, and then we can allow our theta to be in degrees, right? So that's what I'm going to use for this video. If you decide to use radians, that's totally fine. I just find degrees, at least in this context of using this formula, a little bit easier to work with. So let's go and jump into our first example. All right, so we're going to find all of the complex fourth roots of root 3 minus I, and the first thing we're going to do is convert to polar form. So what I like to do is plot this in the complex plane. And remember, this is my real axis, this is my imaginary axis, and the real part of this number is root 3, and the imaginary part is -1. So I'm going to go root 3 along my real axis, and then -1 along the imaginary axis, and this is going to be my point right here, okay? So remember that I'm trying to find r, so that's this distance here between the origin and the point, and I'm trying to find theta, so I'll draw my theta here in blue. That's this angle that wraps all the way around to this dotted line, right? So I need to find r and theta, and I could start by finding r because I can think of this as a triangle, as a right triangle, and then my r is the hypotenuse. So that means that r squared equals root 3 squared plus -1 squared, right? And if you just remember r squared equals x squared plus y squared, that's exactly what this is, right? So r squared equals root 3 times root 3, that's 3, plus -1 times -1, that's 1. So my r squared equals 4, and this means that r equals 2, okay? So not too bad. R usually isn't too tough to find. Now we just need to find theta. So what I'm actually going to do is use tangent, although you could use sine or cosine as well now that we have r. But I'm going to say whatever this angle is, the tangent of this angle equals y over x, right? Or you can think of it as opposite over adjacent. So negative 1 over root 3. And if I rationalize this denominator by multiplying by root 3 over root 3, it may look a little more familiar if you're thinking in terms of exact values. Because then what I get is I'm looking for an angle where the tangent of that angle is equal to negative root 3 over 3. Okay? Since it's a negative, I know it's either going to be in the second or fourth quadrant, but obviously we're in the fourth quadrant. So I'm looking for the angle in the fourth quadrant, and I know that for these kind of root 3 over 3 values, our reference angle is always 30 degrees when it comes to using tangent. So that means I know that this angle here, our reference angle, is 30 degrees. So that means that wrapping all the way around, I'm stopping 30 degrees short of a full rotation. So then my theta in this case is actually going to be 330 degrees. And now we found r and theta. So you could take theta equal to negative 30 degrees, and that would technically work. However, when we use this formula, I like to have my angle as a positive angle measure between 0 and 360, right? So I'm taking this one. So now that we have r and theta, let's see if we can rewrite this number in polar form. All right, so I've taken this number, I've converted it to complex polar form, and now I'm ready to start using this formula to start finding the fourth roots of this number. So I'm going to start by finding my first root, and remember, that's when k equals 0. And what I'm going to take is the nth root of r. So my r in this case is 2, my n is 4, so I have the fourth root of 2. And I'm just going to leave it like that because there's no nice way to simplify that without having to put it in a calculator and round, and I don't want to do that. So then what I have in here is the cosine of theta over n. Remember, my n is 4 and my theta is 330 degrees. So 330 divided by 4, that should give me 82.5 degrees. Okay, plus 360 degrees k over n. Well, my k is 0. So it doesn't really matter what n is. When k is 0, that term is always going to disappear. So I end up adding 0 here. So I can really just forget about that term. And that's always going to be true when we find our first root, when k is 0, is we can just forget about that. So here we just have the cosine of 82.5. And another thing I want to point out is that the argument for cosine and sine, right, the stuff that's in the parentheses, is the same. So once I find this for cosine, I can just write it down for sine. There's no sense in trying to work it out again because I've already found what I wanted to find, right? So I can just copy the rest down and bam, there we go. We have our first root. So let's see if we can find our second one. So that's when k is equal to 1. And the nth root of r, that's always there, right? It doesn't matter what k is. So I can just copy down fourth root of 2. And then I can write out the cosine of, and remember, theta over n, that doesn't change either. So I can write out 82.5 degrees, and all I have to think about is what am I adding now that k is equal to 1, right? So I'm adding 360 degrees times 1 over n. N is 4 in this case, right? So 360 divided by 4, that's 90 degrees. So I'm taking 82.5 and adding 90 degrees, and that's going to give me my argument here. So when I add those together, I get 172.5 degrees. So I'm just going to go ahead and replace this with 172.5 degrees. And remember, once I find the angle that's in the cosine, I can just copy it down for sine. Those are always the same. So plus I sine of 172.5 degrees, and we found our second root. We just have 2 more to go, so I'm going to scroll down. So the next root is when k is equal to 2, and again, we can always just copy it down what's in front here. Fourth root of 2 times cosine of, remember, this is theta over n. That's always going to be 82.5 degrees. We just have to figure out what are we adding now that k is equal to 2. Well, we have 360 times 2, that's 720. Divided by 4, that's going to give us 180 degrees, okay? So when we take 82.5 degrees and add 180 degrees, we should get 262.5 degrees. So I'm going to go ahead and replace this with 262.5. And again, I can copy this down for the sine part as well, plus I sine 262.5, and now we just have one left. And maybe you know that there is a pattern here, and I'm actually going to point that out right now. And one way to see it is that each time we increase k by 1, we could think of this multiplication as repeated addition, right? In other words, look at the difference between the angle in my first root and in my second root, 90 degrees, right? Now look at the difference between the angle in my second root and my third root, 90 degrees. That's always going to be consistent, right? Because each time I increase k by 1, I'm basically just adding another 360 degrees over n, right? In other words, if k is 2, then really what I'm doing is multiplying something by 2, which is like adding it twice. Multiplication could be thought of as repeated addition. So in other words, I'm repeatedly adding this 360 degrees over n, k times, to this angle, right? So if we follow this pattern, what we can notice is that, from each previous root to each next root, we're just taking the angle and adding 90. And that's actually a nice little shortcut. And if you knew that already, then maybe you're frustrated that I worked all of these out by hand the way I did. But since a lot of people watching this video are probably just learning about this formula, I wanted to show me working it all out. But in the future, in the next example, I will use this pattern where we notice that add 90, add 90, add 90. So this is going to give me 352.5 degrees plus I sine 352.5 degrees, and those are all 4 of our complex fourth roots of root 3 minus I. We could convert these to rectangular form. If it was asked in the question, we would just have to use a calculator. I'm going to leave them like this. Usually it's okay to leave them like this, but hopefully that example helped. We're going to do one more and then we'll finish up the video there. Alright, so now we're going to find all of the complex cube roots of -8, and at this point I actually encourage you to pause the video and try this on your own, then press play to compare your work with my work. But we're going to go ahead and start by converting this to polar form. We need it to be in polar form in order to use our formula. And what I see a lot of students get confused about with these kind of examples is where is the imaginary part of this number? And what I like to write this as is -8 plus 0i, and that often clears it up. So my imaginary part is actually 0, right? So I'm going at -8 along the real axis and then 0 on the imaginary axis. So my point is actually here on the real axis. And this is a great example of why I like to plot these in the complex plane, because we can actually visually see what our r and theta is. Remember, our r is the distance from the origin to that point, which is clearly 8, right? This distance is clearly 8 here. And our theta is this angle that takes us out to this line that extends out to -8, right? So in this case, our theta is actually 180 degrees. So it's pretty clear to see both of these, and we didn't even have to really do anything other than just look at the point we plotted in the complex plane. So that's why I like to do this. Now let's see if we can write -8 in polar form. So -8 converting to polar form. So we have r, and then we have the cosine of 180 degrees plus I sine 180, okay? So now this is the number in polar form that we're going to use to find our roots. So first, when k is 0, what do we have? Well, remember, our n is 3. We're finding cube roots, so we're going to have 3 distinct cube roots. Since our n is 3, what's going to be out here is the cube root of 8, which we can actually nicely simplify because that's just 2, right? 2 cubed is 8, so we can replace that with 2. And then what we have here is the cosine of 180 over n. So 180 over 3, which gives us 60 degrees. And remember, that term that we're adding has k in it, and since k is 0, that always disappears when we find our first root. So this is the angle in our first root. And in this example, I'm actually going to employ the shortcut that I mentioned in the last example, that pattern that we noticed. And this all has to do with what 360 over n is. This is what we end up adding each time to get to the angle in our next root, right? In our last example, n was 4, So this was 90, and we notice that we can add 90 each time to get to each next angle. In this case, n is 3. So this is equal to 120. So I can add 120 degrees to get to each angle in our next root. And the reason why this is, again, is because we have a k attached to here in our formula. So when k is 1, we're adding 120 degrees to 60. And when k is 2, we're adding 120 plus 120. That's why I was mentioning that repeated addition. If that didn't make sense, maybe this is a little clearer. So when k is 2, we're adding 120 twice to 60. And that's why we could just add 120 to each previous angle to get to each next angle. Hopefully that makes sense. Let's go ahead and employ this little pattern. You'll see it makes this process a lot quicker because now I can just write this as 180 degrees because that's 60 plus 120. And then my next root is going to have 300 degrees in the argument. And what's out in front here always stays the same, so I don't need to change this at all, right? Because that's just the nth root of r, which never changes. The only thing that changes is my angle, so I can just write this as 180 plus 120, so 300 degrees. And it saves you a little time. And so this is how I usually do it, is off to the side I just write out whatever my 360 over n is, and it really just depends on what kind of root you're finding. And then that's the angle that I add each time to get to each next root. So these are 3 distinct complex cube roots of -8, and what I'm actually going to do for this example is convert each of these to rectangular form, just so we can see what that looks like. And just because it's pretty easy, we actually don't need a calculator because these are all exact values that hopefully we know. Cosine of 60 is 1/2. Sine of 60 is root 3 over 2. My 2's cancel out nicely, so one of my roots is 1 plus root 3i. And now if you remember when you took algebra, we always have these complex conjugate pairs as our roots. So think about that. One of our roots should turn out to be 1 minus root 3i, right? We can kind of look ahead at that. So let's see, if we convert our z1 to rectangular form, we get 2 times, let's see, cosine of 180, that's -1, plus I sine of 180, that's 0. So my I term actually disappears there, and I'm just left with -2. Let me write that 2 a little better. But that should make sense because think about it. -2 cubed is -8. And that's really what we're being asked to find, are all the numbers that we can cube to get -8, right? So that should make sense as well. And then we're expecting this one to be that complex conjugate pair. So we're expecting this to be 1 minus root 3i. But let's double check for sure. Cosine of 300, that is 1/2, plus I sine of 300, that's negative root 3 over 2. So I'll just write it here in parentheses. But once we simplify this, this ends up being 1 minus root 3i, which is what we suspected it would be. And then we have our 3 roots now in rectangular form. So this may not be required, but I think it's cool to kind of relate this to stuff that we've done previously in algebra. And that's kind of one last thing I want to point out, is that we can actually, when dealing with numbers like -8, -27, -1, and we're finding the roots of these, we can actually do this without using DeMoivre's theorem, right? We could have just wrote out, well, what number can I cube to get -8? Because again, that's what we're asking to find here, right? And then what we could have done is solved this equation. This is actually a sum of cubes, right? So if we factor this, we have x plus 2 times x squared plus 2x. Let's see, same, opposite, always positive. So this is actually a minus plus 4 equals 0, okay? When we set this part equal to 0, we get our -2 root. And when we set this trinomial equal to 0 and solve, we get that complex conjugate pair, right? We're going to have to use the quadratic formula, and we're going to get 1 plus or minus root 3i. So pretty cool to relate it to stuff that we've already kind of learned about from algebra. But that's all I really have for this video. Hopefully you found it helpful. This stuff really just takes practice. keep working out examples, keep thinking about this, and keep flexing those brain muscles. And I'll see y'all in the next video.